A warm and pleasant greetings to all. It gives me an immense pleasure to welcome our Secretary, Sri Ashok Kumar Mundraji, and Principal Captain Dr. Santosh Babu sir, Head of the Postgraduate and Research Department of Mathematics, Professor R. Venkatamanan sir, and today's speaker, Mr. P. Thirumal, Assistant Professor, DWARAKA Govardhan Vaishnav College, and all the participants for this first day of a national webinar series 2. One song can change a moment, one idea can change a world, one step can start a journey, but a prayer can change the impossible. Let us begin this session by a prayer song seeking the blessings of the Lord Almighty, followed by Tamil Thai Valthu.
நீராறும் கடலொடுத்த நிலமடந்து கெழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनां नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
I am glad to introduce our eminent speaker of this day, Mr. P. Thirumal, Assistant Professor of Mathematics, DWARAKA Govardhan Vaishnav College, who is going to enlighten us today by his talk on some applications of fixed point theory. With the extensive knowledge that he has on this topic, Sir currently working as Assistant Professor of Mathematics, DWARAKA Govardhan Vaishnav College. He has 6 years of teaching experience. Sir has completed his master degree in mathematics from University of Madras and his MPhil from University of Madras. He is currently doing his PhD in University of Madras. His area of interest is fixed point theory and functional analysis. He had qualified in NET, JRF, GATE, and SLET in mathematics. Sir, it really gives me happy to welcome you, sir. Now I hand over the session to you, sir.
Thank you, ma'am. Ma'am, my screen visible, ma'am?
Visible, sir, visible.
Okay, okay, ma'am. Thank you, ma'am. Okay. Okay, first I would like to thank our head of the department for giving this opportunity. Okay, today I'm going to discuss some basic properties of fixed point and its applications. Okay, we'll start from the basic definition. Okay, definition of a fixed point. So fixed point means, okay, we need a space. So a point x of a space, x is a fixed point of a function x to x. So our function domain and codomain is the same domain, and codomain also the same value. Here x is a same space, that is a domain, and the codomain is the same space. A point x is said to be a fixed point of a function f. It takes a image value same, that is f of x equals to x. Then x is said to be a fixed point of the function f. Okay, this is a basic definition of a fixed point. So fixed point is nothing but the image value same. So if you give a input x, that image value again the same value, means that point is called a fixed point of a function f. Okay, we'll see some examples. Okay, suppose f of x equals to x. This is an identity function. It takes every value is the same value. Suppose if you substitute f of 2 equals to 2, that is f of x equals to x is an identity function. It takes every value is the same value, which means every point is a fixed point of a function. And the identity function, it takes all the points is a fixed point. Suppose some function may not have a fixed point. We'll see that type of example. Okay, suppose I'm taking x equals to r with the usual metric. In this metric, I'm defining a map. T is a map from x to x. Here x is r, that is a map from r to r, defining by x plus a, that is t of x equals to x plus a. It's a translation map. That is, it translates all the elements by a, that is t of x equals to x plus a. It's a simple translation map. This map has no fixed point. So we can say, okay, 1 second. Okay, now I'm taking here a function f. F is a map from r to r. First, I'm defining f of x equals to x. This is an identity function. So identity function means all the points in real line is a fixed point. So it contains infinitely many fixed points, or we can say uncountably many fixed points. That is, all the points are the fixed point of this function f of x equals to x. Since our definition is fixed point means f of x equals to x. So if you substitute the value x, the image value again x, means we can say x is a fixed point of the function f. So I'm taking f of x equals to x, it's identity function. So every point is a fixed point of this function. So we can say a function can have infinitely many fixed points. Suppose now I'm defining f of x equals to x by 2. Same map from r to r. Now f of x equals to x by 2. I need to find the fixed point of this function. So f of x equals to x by 2. It has a fixed point, means it takes the same value x. So x by 2 equals to x. So x equals to 2 times x equals to 2x. So just we can get 2x equals to x. So from this 2x minus x, x equals to 0. So x equals to 0 is the only fixed point for this function f of x equals to x by 2. Now I already said a translation map. So I'm taking here t. T is a translation map. T is a map from r to r, or we can say f is a map from r to r, and t of x is defined by x plus a, provided a is non-zero. I'm taking a is non-zero. Suppose a is 0, means again it becomes a first example, f of x equals to x. It's identity function, it has infinitely many fixed points. So I'm taking here a is non-zero. So t of x equals to x plus a. It's a translation map. So first we'll find the fixed point of this function. So it has a fixed point, means t of x, 1 second. It has a fixed point, means t of x equals to x, which means x plus a equals to a. So from this, x plus a equals to x. From this we can get a value must be 0. But our condition a is non-zero. So a translation map cannot have a fixed point. Suppose it has a translation map T of x equals to x plus a having a fixed point means a value must be 0. Then only this translation map have a fixed point. But this translation map does not have a fixed point. So this function has infinitely many fixed points. Infinitely many fixed point. This having only one fixed point. This function has no fixed point. Now I'm giving one more example. F of x equals to x square. F is a map from R to R. So finding a fixed point means x square equals to x means it has a fixed point. That is f of x equals to x, so x square equals to x. So simplifying this, x square minus x equals to 0. So simply we can write x minus 1 equal to 0. From this we can get x value either 0 or x value 1. So it has two fixed points. X equals 0 and 1 are the fixed points. So it has two fixed points. So we can define a map R to R. Some functions may have infinitely many fixed points. That is identity map. Some function having only one fixed point. We have an example x by 2. It has only one fixed point, namely 0. Some functions have no fixed point, but this is a continuous function. T of x equals to x plus a. It's a translation map. It has no fixed point. It has two fixed points also possible. So a continuous function may have unique fixed point or finite number of fixed points or infinitely many fixed points. Here it's an uncountable number of fixed points. So all the cases exist. So fixed point means here I'm giving an example in R to R. F is a map from R to R. So graph of the function. So first one, f of x equals to x. So this is a line y equals to x. Okay, f of x equals to x means it takes the same value. So this is an overlapping line. So the function y equals to f of x equals to x, overlapping the line y equals to x. So all the points merging in this point. So it has infinitely many fixed points. That is, all the points are fixed points. In the first example. In the second example, f of x equals to x by 2. So f of x equals to x by 2 means its slope value 1 by 2. So y equals to x by 2. So here y equals to mx plus c. So it's a straight line passing through the origin with slope value 1 by 2. So this is a straight line passing through the origin with slope value 1. So y equals to mx plus c. So this is slope value 1 by 2. So this two lines intersecting point is only one point. So namely 0. So x equals to 0. It has only one fixed point. So f of x equals to x by 2 contains only one fixed point. Next, translation map. T of x equals to x plus a. It translates all the points. So it moved to x plus a. Suppose this is a positive value. A is non-zero. I'm taking a is non-zero. Suppose a is positive means it translates the line to this side, or negative value means it translates this side. So these lines never intersect the line y equals to x. So it does not have a fixed point. Our translation map. So this does not intersect with the line y equals to x. So it has no fixed point. This is one, f of x equal to x square. So y equal to x square, it's a parabola. So fourth example is simply it's an equation of a parabola. So it's intersect with the line y equals to x. This is our line y equal to x. So equation of this parabola y equal to x square. This intersect the line y equal to x namely in 2 points. One is x equal to 0, another 1 point. If you are solving y equal to x and y equal to x square, we are getting the point 0 and 1. So this is the intersecting point. X equals 0, here this value 1. So this 2 points, x value here, this value 1. So it has only in this 2 point, namely x equals 0 and x equals to 1. These 2 points are the fixed point. So our idea is so if you want find a function having 3 fixed point means we can find a functions this point. I'm starting from here. So 1, 2, 3. I can find such a graph of a function. This graph intersect only 3 points. So this function having only 3 fixed points. Suppose I need to find a function having 10 fixed point means I can draw a graph, continuous graph, intersecting this line exactly 10 points. So I can draw like this. So after 10 points, I can move upward or downward by continuous map. So I can find a fixed point. I can find a map such that containing unique fixed point or finite number of fixed point, maybe that finite number, any finite number of value fixed points or uncountable number of fixed points. So I can find any number of, I can find a function containing any number of points. Okay, these are all the examples. So second one, x by 2. Third one, x square. This is a parabola. It contains only 2 points, namely 0 and 1 are the 2 fixed points. Next one, this is an identity function. It has infinitely many fixed points. Okay, next. X equal to r. Again, I'm taking the value r. Our space is r under the usual metric. T of x equals to 1 plus x whole power 1 by 3 for all x in r. So finding a fixed point, what is the meaning of finding a fixed point of this function? T of x equals to f is a map from r to r. F of x is defined by 1 plus x whole power 1 by 3. So I'm finding a fixed point of this function. So what is the meaning of finding a fixed point here? Suppose it has a fixed point, means I can find x equals to 1 plus x whole power 1 by 3. It should satisfying this equality, x equals to 1 plus x whole power 1 by 3. So here the rational power, so I just simplified this, x cube equals to 1 plus x. So whole power 3 by 3, this is 1. So this is x cube minus x minus 1 equal to 0. So finding a fixed point of this function is equivalently solving a cubic polynomial, or finding a real root of this cubic polynomial is equivalently finding a fixed point of this function f of x equals to 1 plus x whole power 1 by 3. So for this type of function, finding a fixed point means we can solving some polynomial. So for this, we are solving x cube minus x minus 1 equal to 0. So the solving this cubic polynomial is equivalently finding a fixed point of this function. So here fixed points are the roots of this polynomial. So from r to r means we can find a real root. Suppose if we take c to c means we can find 3 fixed points, since this polynomial having 3 roots. We know that a non-constant polynomial have a root. That is a fundamental theorem of algebra. It's a degree 3, so at most it has 3 roots. Suppose one is a real root, another 2 is complex mean, it occur in a conjugate pair. So we can find r to r means maybe it has 1 fixed point or 3 fixed point in a real. Okay. Okay, next definition, Lipsch is continuous. So we are taking a metric space x. So in a metric, we are defining a function t from a metric space x to x. This map t is said to be a Lipsch continuous, means there is a constant alpha. This is strictly greater than 0. So 0 also not allowed. It must be a positive value, but it takes greater than 1 or any value. Alpha must be greater than 0 and satisfying the condition. So d of tx comma ty less than or equals to alpha times d of x comma y for all the pair x comma y in x. So here alpha strictly greater than 0, and here d is a metric. So we are finding the distance between the images. This is less than or equals to alpha times distance between the points x and y. So this equality satisfied means this function is said to be a Lipsch's continuous map. This map t is called a Lipsch's map. So Lipsch's map means it's satisfying this condition. So from this definition, we can say all the Lipsch's continuous functions are uniformly continuous. Since d of tx comma ty less than or equals to alpha times d of x comma y, we know the definition of continuity. So continuity definition. So f is a map from, I'm giving an example from r to r only for the easy case. So f is a map from r to r. We can say if a function f is said to be continuous from r to r means for given any epsilon positive, there exists a delta positive such that mod f of x minus f of y less than epsilon whenever mod x minus y less than delta. Okay, this is true for all x comma y belongs to the real line R. So uniformly continuous means for a given epsilon, I can find a delta satisfying this equality, mod f of x minus f of y less than epsilon whenever mod x minus y less than delta. This is for all the pairs. This is uniformly continuity definition. So continuity definition means Again, f is a map from R to R for all x belongs to x. Given any epsilon positive, there exists a delta positive such that mod f of x minus f of y less than epsilon whenever mod x minus y less than delta. So this is a uniform continuity definition. This is continuity definition. So what is the difference between these two? Here, this for a given epsilon, I can find a delta satisfying this condition. So this delta depending only on epsilon means this function is uniformly continuous. So for a given epsilon, I need to find a delta. This delta depending only on epsilon means this function is uniformly continuous. For a continuity, for a given any epsilon positive, I can find a delta. This delta depending on epsilon as well as the point x. So depending on epsilon and the point x means we can say it's a continuous function. But in a uniformly continuous, delta depending only on epsilon. This is a uniformly continuity. And continuity we can speak at a single point also. At a point x equals to a, we can speak a continuity at a single point also. But uniformly continuous means we can speaking about a continuity uniformly continuous at a point x equals to a. This is meaningless. We cannot discuss at a single point. So in some domain or region or some disk, we can define some neighborhood at that point. We can say it's uniformly continuous in this neighborhood. In a single point, we cannot define a uniformly continuity. But continuity we can define a single point. Okay. So here our definition. Lipschitz continuity means d of tx comma ty less than or equals to alpha times d of x comma y for all the pairs x comma y belongs to our space x. Okay, now for a given epsilon, I can take the same epsilon is a delta value. Then I can find this is less than or equals to d of x comma y less than or equals to delta. I need to take d of x comma y less than or equal to delta. I'm dividing by alpha. This alpha value strictly greater than 0. So I can divide by alpha. This is possible. Alpha value 0 means we cannot take this. Alpha value greater than 0 means I can dividing by this alpha. So this is my delta. Or I'm taking here epsilon. For a given epsilon positive. So always epsilon value must be positive. Here alpha value must be greater than 0 in a Lipschitz condition. So epsilon by alpha is again a positive value. So d of x comma y less than or equals to epsilon by delta. Sorry, epsilon by alpha. This is my delta value, epsilon by alpha. Now from this we can get d of tx comma ty value less than alpha times d of x comma y less than or equals to epsilon by alpha. So this is epsilon by alpha. Alpha cancel. I'm getting for a given any epsilon positive. So epsilon greater than 0 is given. I can find a delta. My delta is epsilon by alpha. Epsilon by alpha. From this, I'm getting d of t of x comma d of y less than epsilon whenever d of x comma y less than delta. My delta is epsilon by alpha. So this is a uniform continuity definition. So all the Lipschitz maps are uniform continuous functions. So by the definition, we can get. So given epsilon, I can find a delta. Delta is equivalently epsilon by alpha. This will work for all the Lipschitz continuous function. So Lipschitz continuous functions are uniformly continuous functions. Okay, from this definition, here alpha is mostly just strictly greater than 0. Suppose alpha value 1 means. Alpha value is 1 means this function is said to be non-expansive map. Just it's a name. Alpha value 1 means d of tx comma ty less than or equals to d of x comma y. It's a non-expansive map. Suppose if alpha belongs to the open interval 0 to 1 means t is said to be a contraction map. So we are assigning a different name for based on the value alpha. If alpha is strictly greater than 0 means it's a Lipschitz continuous. Alpha value 1 means it's a non-expansive map. Alpha value lies in between 0 to 1 means it's a contraction map. Next, if this distance strictly less than d of x comma y, image's distance is strictly less than the point distance means whenever x is non-zero, then t is said to be a contractive map. So contraction map means alpha value lies in between 0 to 1. Contractive means this is strictly less than d of x comma y. Okay, now again we can see a contraction map is a contractive map. From the definition we can conclude this. That is d of tx comma ty less than or equals to alpha times d of x comma y. This is for all the point x comma y belongs to x. Okay, this is if suppose alpha belongs to the open interval 0 comma 1 means we can say it's a contraction map. Contraction map means alpha value lies in between the open interval 0 to 1. So d of tx comma ty, I'm dividing by d of x comma y. When I can divide, this distance never be 0. So never be, when the distance between the 2 point x comma y equal to 0 implies the point must be same point. D of x comma y equal to 0 means x must be equivalent to y. This is the basic definition of a metric space. So I'm dividing means I can assume x not equals to y. Then only I can dividing by this value d of x comma y. So dividing by this value, I'm getting this value alpha. So d of tx comma ty dividing by this value d of x comma y provided x is non-zero. Now I'm getting less than or equals to alpha. This alpha value belongs to the open interval 0 comma 1. So I can say this is strictly less than or equals to 1, or I can say it's a strictly less than 1. This alpha value belongs to the open interval 0 to 1. So this alpha value must be less than 1. So now I have d of tx comma ty strictly less than d of x comma y. So from the contraction map, I can write this is a contractive map. Provided x is non-zero, x not equals to y means this is possible. Since suppose x value 0 means this image value 0. 0 less than some value. Distance never be 0. So this is a positive value. Never be less than 0. So this is not possible. So we are assuming here x is not equals to y. So distinct point, x and y are distinct points. Then a contractive map is a contraction map is a contractive map. So we can conclude every contraction map is a contractive map. What about the converse part? Contractive map is a contraction map. Now example of a map which is contractive but not contraction. The converse is not true. So I can write a function which is contractive but not a contraction map. So this is in a simple example. I'm taking my space x is a closed interval 0 to 1 by 2, that is 0 to 0.5. So the length is of the interval length is just 0.5. So x is 0 to 1 by 2 with the usual metric. I'm defining a function x to x, that is 0 comma 1 by 2 to 1 by 2 by x square. This is my map. I can show this is a contractive map. So contractive map means this absolute value, that is a distance between tx and ty, strictly less than x minus y. We can do this. So absolute value of x square minus y square equals to, this is a square minus b square. So a minus b into a plus b. This is strictly less than mod x minus y. The reason is x plus y. X and y lies in between the interval 0 to 1 by 2. If x is not equals to y means I cannot take the same value 1 by 2 both times. So if it choose any 2 points, that point never be equal. That is any 2 distinct point, the sum value less than 1. So x plus y value less than 1. So you are multiplying x minus y, multiplying with this a small value that is less than 1 means this quantity is again less than mod x minus y. So here x square is t of x, y square means t of y. So mod tx minus ty strictly less than mod x minus y for all x comma y belongs to x, provided x is not equals to y. Now this is a contractive map. So in this space 0 to 1 by 2, t of x equal to x square is a contractive map. But it's not a contraction map. Contraction map means there is an alpha. This alpha value lies in between the open interval 0 to 1, satisfying this equality, this inequality. So t of x minus t of y less than or equal to alpha times x minus y. I can choose x value is 1 by 2, y value is 1 by 2. In a contraction map, we can take the same value also possible. So if I choose x value 1 by 2 and y value 1 by 2, t of x minus t of y, we are getting here x plus y value must be less than or equals to alpha. Actually, this is my map is t of x equals to x square. So absolute value of x square minus y square. This is equivalently x minus y and x plus y. Here x value and y value belongs to the closed interval 1 by 2 and x comma y not equals to, that is distinct point. X and y are different points. Then This is strictly less than mod x minus y. We prove t of x minus t of y strictly less than mod x minus y, provided x is not equals to y. This is a contractive map. So contraction map means this value is strictly less than x minus y. So x plus y, this x plus y value strictly less than alpha. But here the alpha value is, here alpha value strictly less than 1. Since I'm taking x value 1 by 2, y value 1 by 2 means I'm getting 1 by 2 plus 1 by 2. This value is 1. So 1 is strictly less than 1. This is not possible. Suppose it's a contraction map means t of x minus t of y less than or equals to alpha times mod x minus y. From this we can get mod x plus y value less than or equals to alpha. Since here this value is mod x minus y, from this we are getting mod x plus y less than or equals to alpha. Alpha value strictly less than 1. But if you choose x value 1 by 2 and y value 1 by 2 means I'm getting LHS value 1. So 1 is strictly less than 1. This is not possible in this map. So it's not a contraction map. So this is an example of a contractive map, but not a contraction. Okay, next a theorem, Brouwer fixed point theorem. So I'm not going to prove this theorem. I will give the explanation, or will prove at least one-dimensional space. I will give a proof of this theorem. Okay, Brouwer fixed point theorem. Every continuous map from F is a map from Dn to Dn. Here d power n is defined by x belongs to Rn. It's a n-dimensional space. Norm x value less than or equals to 1. In a non-linear space, norm x less than or equals to 1 means it's a unit ball. So in a one-dimensional space means, okay, for simple example, I take here R to R. F is a map from R to R. R to R means this Dn become a just an interval, closed interval 0 to 1. Okay. So every continuous map Dn to Dn has at least one fixed point. So this is a Brouwer fixed point theorem. It has at least one fixed point. Maybe it has 2 fixed point, 3 fixed point, or finite number of fixed point, or infinitely many fixed point, uncountably many fixed point. Everything is possible, but it has at least one fixed point. So Brouwer fixed point theorem says that a continuous function from Dn to Dn has at least one fixed point. Here Dn is defined by x belongs to Rn, norm x less than or equals to 1. So in a one-dimensional space, it's in a closed interval. In a two-dimensional space, it's a disk. In a three-dimensional space, it becomes a sphere. In a four-dimensional space, it's increasing. It's n-dimensional space. So we can visualize in a one-dimensional space is a closed interval. Two-dimensional space, it's a circle. In a three-dimensional space, it's a sphere. Okay. So I will give a simple proof for one-dimensional space. Okay, so Brouwer fixed point theorem says that F is a map from a closed interval. I can take 0 to 1 or a comma b2. I'm taking the closed interval a comma b2, closed interval a comma b. I'm taking a, b, or any real number a comma b2, a comma b. Okay. Now we need to prove a continuous function from a closed and bounded interval. This is a compact space. Closed and bounded interval to closed and bounded interval, compact set to compact set. A continuous function, f is a continuous function from a compact set. Okay, suppose I'm taking a minus f of a value less than or equals to 0, or 1 second. Next, b minus f of b value greater than or equal to 0. So either these two cases is possible. This is our function y equals to x. So I'm taking here a value 0. For simplification, I'm taking here a value is 0 and b value is 1. So this is 1. Okay. Here f is a continuous function. So a minus f of a value less than or equal to 0 means that b minus f of b value greater than or equal to 0. Or reversely, we can say b minus f of b value less than or equal to 0, or a minus f of a value greater than or equal to 0. So I am assuming this value, this condition, a minus f of a value, this a value and f of a value. If suppose it is increasing function means a minus f of a value less than or equal to 0, or we can get greater than or equal to 0. This is based on the increasing and decreasing function. Okay, I'm assuming this a minus f of a less than or equal to 0 and b minus f of b value greater than or equal to 0. Now I'm defining a function g from a closed interval a comma b to r, defining by g of x equals to f of x minus x. Okay, here f is a continuous function. I'm defining a map g is a map from a comma b to r. G of x is defined by f of x minus x. Here f is a continuous function minus x, or we can say x is a continuous function. F of x equals to x. It's an identity function. It is continuous function. Sum of two continuous function is a continuous function. So f of x minus x is a continuous function. So f is a continuous function minus x. Again, it's a continuous function. Sum of these two functions is a continuous function. So g of x equals to f of x minus x. So here, what is the g of a value? G of a value, a minus, that is f of a minus a value. G of b value, f of b minus b. So a minus f of a less than or equal to 0 means f of a minus a value greater than or equal to 0. So this is greater than or equal to 0, or this is less than or equal to 0. So g of a value greater than or equal to 0, or g of b value less than or equal to 0. Any one case is possible. This is greater than 0 means this is less than 0, or this is negative value means this is positive value. So g of a takes positive value means this is negative value, or this is positive value means this is negative value. Okay, by the intermediate value theorem, we can say there exists a point such that this function taking the value 0. So one case, this is a positive value one side, on the side this is a negative value. So by the continuity, g is a continuous function, so it touches the x-axis. So it takes a value 0 at some point. So there exists a point, say x0, such that this function takes 0, that is g of x equal to 0. By the intermediate value theorem, there exists a point x0 such that g of x equal to 0. So g of x value 0 means f of x minus x, this value must be 0. So that is f of x equals to x. So there exists a fixed point. F of x equals to x means x is a fixed point of the function f. So from this we can conclude any continuous function from a closed interval a comma b to a comma b as a fixed point. This is for any closed interval a comma b. This is a one-dimensional case. Every continuous function having a fixed point. This is a simple proof for a one-dimensional case. We can prove for two-dimensional space, three-dimensional space. For any n-dimensional space, this is true. For, or we can generally, we can say a space, any compact convex set to a compact convex set having a fixed point. Suppose in a three-dimensional space, I'm taking a unit sphere. So unit sphere to unit sphere, there is a map, f is a map from unit sphere to unit sphere. Here norm x value less than or equals to 1. It's a 3 tuple x1, y1, z1. This norm value less than or equals to 1 means it's a unit sphere. So unit sphere to unit sphere, or we can take any constant k. Norm x less than or equals to k, norm x less than or equals to k means it's a convex compact set to a convex compact set having a fixed point. This is a Brouwer fixed point theorem. Generalized Brouwer fixed point theorem says that every continuous function from a compact convex set to a compact convex set having a fixed point, having at least one fixed point. Maybe the fixed point is a finite number of fixed point or infinitely many fixed point also possible, but it has at least one fixed point. Okay, using this Brouwer fixed point theorem, I'm going to prove a fundamental theorem of algebra. Already you know the proof of fundamental theorem of algebra. In algebra, you are proving a different method. Here, using a fixed point theory, we are going to prove the fundamental theorem of algebra. That is, this theorem says that any non-constant polynomial having a root. So if we take without the constant polynomial, any non-constant polynomial having a root. So I'm taking p of z equals to a0, a1, z, an, z power n, provided an is non-zero. If an is 0 means it becomes reduced to a constant. So I'm assuming an is non-zero. It's a complex polynomial. Then there exists a point z0 in a complex plane C such that p of z0 equal to 0. That is, z0 is a root of this polynomial p of z. So every non-constant polynomial having a 0 in the space. So this is a fundamental theorem of algebra. This theorem I'm going to prove using the fixed point theorem. Okay. So first I'm assuming an value is 1. That is the highest in this polynomial. An is a highest degree z power n, nth degree polynomial. that coefficient an value, I am assuming 1. Suppose it is not 1 means I am dividing throughout this polynomial by this value an. I am getting this coefficient is 1. So here for simplification, I am taking an value is 1. That is the largest degree coefficient. I am taking an value 1. And z is r e power I theta. This is a polar form. R is the absolute value of z. Theta is the argument of that z. So z can be written as r e power I theta. Theta value lies in between 0 to 2 pi. Now I am defining the value r. So capital R is, I am taking the absolute value, sum of all the absolute value of the polynomial. So this is my polynomial a0, a1, a2, z square, a3, z cube, etc. an, z power n. I am taking this coefficients a0, a1, a2, etc. an. Absolute value of this coefficient plus I'm taking some extra. This is greater than that value. So I'm just taking 2 plus or 3 plus some value. That is the sum value. I'm taking greater value, that coefficient sum value. So just I'm taking 2 plus, or we can take 5 plus 10 plus any value. Okay, this is my r. Now I'm defining a function. G is defined by z minus p of z. Okay, I will write this function. My function G is defined by z minus p of z divided by r e power I n minus 1 theta, provided mod z value here less than or equals to 1. Suppose mod z value greater than or equals to 1 means, that is inside the unit disk, mod z less than or equals to 1 in a complex plane, defining like this. Suppose outside the unit disk, that is mod z greater than or equals to 1 means I am defining a function z minus p of z divided by r z power n minus 1. This is my function G. So G of x is defined by like this. Here this map G is a map from complex plane to a complex plane. Okay, first we need to check this function is continuous function or not. So z is a continuous function. Here p of z is a polynomial. So p of z equals to a0 plus a1z plus a2z square plus etc. plus an z power n. It's a polynomial. Every polynomial is a continuous function. So this is a continuous function dividing by some value. When it takes a 0 value, r value. So I'm assuming what is my r value? R is 2 plus some all the absolute value. So r never be 0. So 2 plus some, again it's, suppose these values are small value means again I'm adding 2 plus. So it's a non-zero value. So here r is non-zero value. E power I n minus 1 multiplying by theta. So exponential function never vanish. So e power this value is never be 0. R is non-zero. So this denominator value is non-zero. So dividing by non-zero is possible. This is a constant. Exponential function is a continuous function. So it never takes 0. So f is a continuous function. G is a continuous function. Provided g not equal to 0 means we can say f by g is a continuous function. So this is a continuous function. P of z divided by r e power I n minus 1 into theta. This is a continuous function. Z minus sum of two continuous functions. Z f of z equals z is an identity function. This is continuous function. So sum of these two continuous function is a continuous function. So this part is over. Mod z less than or equals to 1 means this is a continuous function. Suppose mod z greater than or equals to 1. That is, we are defining a in two types. One is inside the unit disk. Inside the unit disk, I am defining like this. Outside the unit disk. So mod z greater than or equals to 1 means outside the unit disk, I am defining like this. Z minus p of z divided by r z power n minus 1. So p of z again, numerator, this is maybe it takes a 0 also possible. P of z 0 means this whole term is 0, but denominator never be 0. R is already we proved it's a non-zero, since r is a 2 plus absolute value of the coefficient value. So r is non-zero. Z power n minus 1. Here mod z value greater than or equals to 1. So this is never be 0. So again this denominator value non-zero. So again this is a continuous function. Mod z greater than or equals to 1. So inside this is continuous function. Outside also it's a continuous function. What about on the boundary? So mod z equals to 1. So on a boundary we need to check. Mod z equals to 1 means it takes a value, this value or this value. So we need to check G is a continuous on its boundary. So mod z equals to 1 means it both take the same value. So this takes a value z minus p of z divided by r e power I n minus 1 theta. So if it mod z value 1 means argument value r e power I theta, this absolute value 1. That is, it takes a value 1. Again z power n minus 1, mod z greater than or equals to 1 means we are defining like this. Suppose mod z value 1 means z power n minus 1 value. So mod z power n minus 1. This value also takes a value 1. So r z power n minus 1. So both the cases, it takes the same value. So on a boundary, this is a continuous function. Z minus, it takes the same value on its boundary. So G is a continuous function from a complex plane C to C. So I'm defining a continuous function using a polynomial P of Z. So our aim is to show that P of Z as a root. This is our aim. We need to prove the polynomial as a root. So for this, I'm defining a continuous function G from a complex plane C to C like this. I'm dividing two cases. One is inside the unit disk, other one is outside the unit disk. Okay, next, by simplification, I'm taking here C. C is set of all points Z belongs to C, mod Z less than or equals to R. So here I'm taking this radius value is R, not a unit disk. I'm taking this radius value R. Here my R is 2 plus absolute value of A0 plus absolute value of A1 plus absolute value of AN. This is my R. So this is a compact convex set. So my C is set of all points Z such that mod Z value less than or equals to R. Here R is defined like this. I'm collecting those points in the set. So C is the convex compact set. This is my set C. Okay. Now by simplification, I can show that two cases, mod Z less than or equals to 1. So there are two cases. Mod Z less than or equals to 1 means I'm finding this absolute value of G of Z. This is by simplification, I can show this is strictly less than R. This is very simple one. So just taking this absolute value. So Z minus P of Z by R e power I n minus 1 theta. I can split this. This denominator value is R less than or equals to some R. So less than or equals to 1 plus the numerator value, absolute value of the polynomial P of Z. P of Z can be replaced by 1 plus A naught, etc. by an minus 1. This value less than or equal to this value. Again, I'm taking this value. This denominator value is greater than the numerator value. So again, this is less than or equals to 1. So this is less than or equals to 1 plus 1 equals to 2. 2 is strictly less than R. Since I'm taking this R value is greater than 2. So now mod G of Z value strictly less than R. Similarly, we can prove mod Z greater than or equals to 1. Outside this value also, I can prove mod G of Z less than or equals to R. This is a simplification. You can do your own. So in the both cases, mod Z less than or equals to 1 means mod G of Z value less than or equals to R. Mod Z greater than or equals to 1. So again, I'm taking the absolute value. Again, I'm splitting this. I'm substituting P of Z value A0 plus A1 Z A n minus 1 Z power n minus 1. I'm taking Z outside here. And again, splitting the modulus value, mod A plus B less than or equals to mod A plus mod B. Again, splitting this, I'm getting this. So by simplification, again, I'm getting less than or equals to R. That is, C is an invariant set for G. So here invariant means F is said to be an invariant map from, here our map is G. So G is a map defined from a complex plane to complex plane. I'm defining a capital C is defined by set of all complex numbers Z such that mod Z value less than or equals to R. Here my R is defined by 2 plus mod A0 plus etc. mod AN. This is my R. So invariant means the complex plane, whole complex plane, this points mapped into the set C. This is my set. Here radius is R. So we proved here mod Z less than or equals to 1 means this absolute value less than R. Again, mod Z greater than or equals to 1 means also this absolute value less than or equals to R. So for all the complex value, this is mapped into the set C. So invariant set means K to K means all the points in this set K mapped into the point K. That is, G of K is contained in K. K is a set defined like this. Or we can use here C, our definition by C. So G of C, where here C is this set. This image of the set is contained in C. Our set is C. So this is an invariant map. So invariant map means A is a set means under this some function f of A contained in A. So F is a invariant map in the set A. So f of B contained in B means we can say F is a invariant invariant under the set B. Similarly, here G of C contained in C, we can say G is an invariant map under the set C. Okay, already we proved G is a continuous function. So G is a continuous function from C to C. It's a continuous. Next, we proved this is an invariant function. Invariant function. So invariant means I can restrict this map to C, where C is Z set of all mod Z less than or equals to R. So C to C. Again, it's a restricted function is also a continuous function. This is not a complex plane. It's my capital C. Just C is defined by, this is a complex plane C. This is my restricted domain. Convex C is a compact convex set. Closed and bounded in a finite dimensional case is a compact set. It's a convex set. So compact convex set. So G is a map from C to C. Here C is a compact convex set. It's an invariant map and it's a continuous function. Now, by Brouwer fixed point theorem says that a compact convex set having a fixed point. So it has a fixed point. So it has a fixed point means this function having a fixed point. Either this case or this case, it has a fixed point. So fixed point means J of Z equals to Z. So our definition, G of Z is defined by, one is Z minus P of Z divided by R e power I n minus 1 theta mod Z less than or equals to 1, and Z minus P of Z divided by R Z power n minus 1. Okay, this is Z power n minus 1. Now we proved this map is a continuous map and invariant map from C to C. That is a compact convex set to compact convex set. It's a continuous function and invariant. So by Brouwer fixed point theorem, it has a fixed point. So it has a fixed point means G of Z value, Z for some Z belongs to C. So it has some fixed point, at least one fixed point by Brouwer fixed point theorem. Suppose Z is a fixed point means it takes the same value. Suppose mod Z less than or equals to 1 or mod Z greater than or equals to 1. Suppose this as a fixed point in this region. Suppose inside the unit disk, it has a fixed point means Z minus P of Z divided by R e power I n minus 1 theta equals to Z. This value is Z. When it becomes Z, this value is equal to Z means it becomes 0. This value becomes 0 only. We can say Z minus this value is 0. So this is 0 means from this we can get the denominator value. R is non-zero. Exponential function never be 0. So P of Z must be 0. So P of Z equal to 0 means here Z is a root of this polynomial. Similarly, for this case, mod Z greater than or equal to 1. Outside the unit disk, it has a fixed point means Z minus P of Z divided by R Z power n minus 1. Here mod Z greater than or equals to 1. It has a fixed point means this value is equal to Z. So this Z cancel, which means this value must be 0. That is P of Z divided by R Z power n minus 1 value must be 0. But Z power n minus 1 never be 0 since our domain is mod Z greater than or equals to 1. So only the possibility P of Z value must be 0. So P of Z value 0 means Z is a root of this polynomial. So both the cases, suppose the fixed point lies inside the unit circle also, it has a root. Outside the unit circle, the fixed point lies outside the unit circle also, it has a root. So both the cases, it has a root. So we proved P of Z equals to 0 for some Z belongs to C. So it has a root in a complex plane. So here arbitrary polynomial a0 a1 z a n z power n. I'm defining a continuous function from a convex compact set to convex compact set by Brouwer fixed point theorem. I can say it has a root. So it is satisfying the relation. So P of Z not equal to 0. So in both the cases, it has a root. So using fixed point theorem, we proved every non-constant polynomial as a root. That is a fundamental theorem of algebra. Okay, next. Next one, Banach contraction principle. Okay, now the Banach contraction principle says that X comma D be a complete metric space. So in a complete metric space, a contraction map having unique fixed point. So Brouwer fixed point theorem says that in a compact convex set having a fixed point, maybe this at least one fixed point. The fixed point may be unique or finite, infinite, any cases. But Banach contraction principle says that in a complete metric space, contraction map means already we proved, we define contraction map d of tx comma ty less than or equals to alpha times d of x comma y. Alpha lies in between the open interval 0 to 1. That is a contraction map. So in a complete metric space, contraction map having unique fixed point satisfying tx equals to x. So contraction principle says that in a complete metric space, contraction map having a unique fixed point. Okay, this is a remark. Here, complete metric space is important. Suppose I'm taking incomplete metric space, 0, 1 is not a complete metric space. Since here 0 is a limit point, 1 is a limit point, so it is incomplete metric space. So in this metric space, I'm defining a function t of x equals to x by 2. Already we proved t of x equals to x by 2 is a contraction map. Simply we can take 1 by 2 is alpha value 1 by 2. If you took alpha value 1 by 2, t of x minus t of y less than or equals to 1 by 2 times x minus y. We can get alpha value 1 by 2. So this is belongs to the open interval 0 to 1. So x by 2 is a contraction map, but it has no fixed point. Since x by 2 having a fixed point 0, 0 does not belongs to our space. So in a Banach contraction principle, completeness is very, very important. That is, in a complete metric space, it has a unique point. Suppose the completeness, if you omit this completeness, a contraction map may not have a fixed point. Okay. This is a Banach contraction principle. Proof is very simple. We can define a sequence, defining a Cauchy sequence. Then in a complete metric space, every Cauchy sequence has a convergent subsequence. That limit point is a fixed point of this contraction map. Proof is very simple. I'm not going to prove this. So this is a Banach contraction principle. Next to this examples, suppose t is not a contraction, but t square may be a contraction. This type of examples also possible. I'm taking x equals to r with the metric, usual metric. T is a map from x to x, and t of x. I'm defining t of x equals to 1 if x belongs to q. That is a rational number. X is a rational number means image value 1. Otherwise, it's a irrational number means this function value 0. This is my t of x. This is a discontinuous function. Nowhere continuous. All the points it is discontinuous. So it's not a contraction map. Already we proved a contraction map means it's a uniformly continuous function. Not only continuous, it is a uniformly continuous function. But my t is not a continuous function, so it's not a contraction map. Now I'm taking t square of x. So t square of x means t of x. So t of one value, t of x value 1. So t of one value again 1. Suppose x belongs to q means t of x value 1. So t of one value again 1. So since 1 is a rational number, it takes a value 1. Suppose it's an irrational number, r minus q. It's an irrational number means t of 0 value 1. Since t of x value takes 0, t of 0 is a rational number. So again, it takes a value 1. So t square x equals to identically 1. For rational number, it takes a value 1. Irrational number, it takes a value 1. So for all the points, the image value 1. So it's a continuous map, uniformly continuous map. It's a contraction map. So t square is a contraction map. But t square and t have the same fixed point. See here, 1 is a fixed point. If rational number 1, if for the rational number 1, the function value 1. So 1 is a fixed point. For t square also, 1 is a fixed point. So t is not a contraction, but t square is a contraction. This type of case also possible. That is, a map is not a contraction map, but t square is a contraction. Some maps, t is not a contraction, t square is not a contraction. Some finite stage, after some finite stage, it becomes a contraction map using this t square, t cube, t power 4, etc. So after some finite stage, it becomes a contraction map. Okay, next, theorem. So we'll see some applications. So this theorem is already, you know some different cases. Uniformly continuous function means derivative bounded. Bounded derivative means a function is bounded derivative having means it is a uniformly continuous function. So similar result for this theorem. Suppose x equals to a comma b is a metric space, usual metric. It's a differentiable function. Then t is a contraction mapping on x if and only if there is a real number alpha strictly less than 1 satisfying t dash of x less than or equals to alpha. That is, its derivative is bounded and alpha value strictly less than 1. So a map is contraction means its derivative is bounded by 1. Suppose if a continuous function is differentiable, differentiable function derivative is bounded by alpha and alpha value less than 1 means we can say it's a contraction map. So this is verification of a given map is contraction or not. Using this also we can verify. That is, a derivative is bounded means and the bound is less than 1, then we can say the map is contraction map. This is if and only if. Contraction map means it has a bounded derivative. Bounded derivative means the map is a contraction. Here, this bound is less than 1. Okay, next, we'll see some applications. I'm not going to prove this, just I will give an idea. System of linear equations. So using fixed point theorem, we can prove a system of linear equations or ordinary differential equation and integral equations. I'm going to explain only these 3 topics only. Within 10 minutes, I will complete this. Okay, first we'll see system of linear equations. So I'm taking a system of linear equations, a11 x1, a12 x2. This is a system of equation. I'm taking n equations with n variables. This system can be written as x1 equals to, just add and subtracting the value a11. So x1 can be written, adding x1 both sides, x1 left side and right side, I'm adding just x1. So x1 can be written as 1 minus a11 x1 minus a12 x2. So similar cases plus b2. Just this, I'm moving right side. So I'm rewritten this equations like this, x1, x2, etc. up to xn. Now I'm defining some coefficient, alpha ij. Alpha ij is defined by aij plus delta ij, where delta ij is a Kronecker delta. 1 if I not equal to 1. Different value means it takes the value 0. Same value means I'm defining 1. So delta ij value is 1 for provided I equal to j. Different value means 0. So alpha ij equals to minus aij plus delta ij. This is delta ij definition. So using this constant coefficient values here, I can simplify this. Xi equals to summation j equals to 1 to n alpha rj xj plus bi. So this equation I can rewritten in this format using this delta ij symbol. If x value is a n tuple in Rn, then I'm taking the coefficient of these equations. I'm written alpha 11, alpha 12, alpha 1n, alpha 11. This is defined by alpha ij is defined like this. So using this notation, I can write capital A. It's a m cross n matrix, n rows and m columns. So this is my matrix A, and I'm taking the b1, b2, bn belongs to Rn. Then the system of equation can be reduced to x equals to ax plus b. That is, this is a given system of equation. This system I'm reducing x equals to ax plus b. Okay, this is a simple transformation. Ax multiplying by a, maybe it's a magnification or contraction, plus some translating by b. B is b1, b2, bn, n tuple in Rn. Okay, next, solving this system of equation is just finding a fixed point of this translation map, x equals to ax plus b. That is, T is a map from Rn to Rn, defining like this, x equals to ax plus b, provided a is this matrix and b is b1, b2, etc. bn belongs to Rn. So finding a fixed point is the solution of this system of linear equation. If T is a contraction map, means it has a unique fixed point. Maybe the system of equation, some cases having a unique fixed point, or it has no solution or infinitely many solutions. Everything is possible. So system of equation can be reduced in this format, x equals to ax plus b. Then I'm defining a map capital T, Rn to Rn, defining T of x equals to ax plus b. Suppose T is a contraction map, means by Banach contraction principle, it has a unique fixed point. Since our space Rn is a complete space, any finite R is a complete R2, R3, Rn is complete space. So Rn is complete in a complete metric space. This map ax plus b is a contraction map, means it has a unique fixed point. Suppose T is a contraction, means it has a unique fixed point. So based on this matrix A, the solution is will vary. So the system of equation can be reduced in the format ax plus b. Then finding a fixed point of this map will give the solution of the system of linear equation. This is one idea. Next, application to integral equation. So I will explain the concept only. So integral equation. So this is a Volterra integral equation. F of x equals to pi of x plus lambda times integral a to x k x comma y f of y dy for all x belongs to the closed interval a comma b. I'm changing the space. My space is a function space. Function space means I'm taking a set of all continuous functions on the closed interval a comma b. In this function, I'm defining a function f of x equals to pi of x plus like this, where lambda is a parameter. This is called the Volterra integral equation. Okay, for this Volterra integral equation, we need to find the solution. How to find the solution? For this function, we need to define a space, complete metric space to a complete metric space. We need to define a contraction map. By Banach contraction principle, it has a unique fixed point. That fixed point will give the solution of the Volterra integral equation. Okay, this is a theorem. For each lambda belongs to R, the Volterra equation has a unique solution F that is continuous on A comma B. So it has a solution. That solution is a continuous function on A comma B. Since our space is a set of all continuous functions, function space. So in a function space, all the points are functions. That solution must be a continuous function. Okay, this is also a very simple proof. I'm not going to prove this. I will skip this. So just we are defining t of f of x. This my map is t of x. My point is a function f of x. So t of f of x is defined of x plus lambda times integral a to x k x comma y f of y dy. This is my function. This function I can prove this is a contraction map from x to x. My x is set of all continuous function on the closed interval a comma b. So in this space x, I can prove this is a contraction map. Then the restricted map, actually this is a complete space C of A comma B. By the Banach contraction principle, it has a unique fixed point. That fixed point will give the solution of this Volterra integral equation. I will skip this. Okay, next, application to differential equation. So for ordinary differential equation, dy by dx equals to f of x comma y with the initial condition y of x naught equals to y naught. This is a given ordinary differential equation. For this, just I will give the theorem only. Let f of x comma y be the continuous function with two variables on a rectangle. This is a rectangle, a length breadth c a to b and c to d. That is x varies from a to b and y varies from c to d. I'm taking a rectangle a. So in this rectangle, f is a continuous function in this rectangle and satisfying the Lipschitz condition of the second variable. So second variable here y1 and y2. So in second variable, it's satisfying the Lipschitz condition means mod f of x comma y1 minus f of x comma y2 less than or equals to cube times mod y1 minus y2. In the second variable y1 and y2, it's satisfying the Lipschitz condition. Okay, for some q greater than 0, for Lipschitz condition, q value must be greater than 0. Next, this solution, it has a solution in the interior of the rectangle A, that is x naught y naught be a interior point of A. Then the differential equation dy by dx equals to f of x comma y, y of x naught equals to y naught, having a unique solution. This is a proof. This is a theorem. I'm not going to prove this now. Okay, I will stop now. So the applications here, there are many applications. I plan to discuss here. System of linear equation. So system of linear equation means the system reduced to a map ax plus b. Then using Banach contraction principle, we can say, suppose the map reduced map is a contraction map, means the system of linear equation has a unique solution. Ordinary differential equation also we can use the Banach contraction principle. Integral equation, that is the integral Volterra integral equation, we can use here. This is my map. If you want, you can try. This is my map. Using this map, we can prove this is a contraction map under the complete metric space C of A comma B. We can prove this Volterra equation as a unique fixed point. This is also simple only. We need to prove T of f of x minus T of g of x less than or equals to some constant times f of x minus g of x. That is our idea. Then it has a solution. Okay, I will stop now. If you have any questions, post in chat box. Okay, thank you. Invariant means, yes, invariant in a function. Invariant means yes, invariant. Suppose f is a map invariant under the set A, means f of A is contained in A. So the space may be different. In a space X, A is a subset of X. Then the map f is invariant under the set A, means f of A contained in A. Then we can say the map is invariant map under the set A. Domain, codomain may be different. So under the subset, we can say it is a invariant map. So A, B, C are a subset of a space X. Then we can say f of A contained in A means f is a invariant map under the set A. F of B contained in B means the function f is invariant under the set B. So need not be same. Domain, codomain may be different. Under the subset, we can define a invariant map. Okay. Any other questions?
Any other questions? Participants, you can post your questions in the chat box.
Okay, ma'am, I think no questions in chat box.
Sir, I think there is no questions from the participants, sir. I think we can conclude our session. I extend my heartfelt gratitude to our secretary Ashok Kumar Mundraji, Principal Captain Dr. Santosh Babu sir, Head Postgraduate and Research Department of Mathematics, DG Vaishnav College, Professor R. Venkatamanan sir, for their constant support and encouragement. My sincere gratitude to our resource person, Mr. P. Thirumal, Assistant Professor, DG Vaishnav College, for sharing his depth knowledge on some applications on fixed point theory. Really, this session is very useful and interesting, sir. Thank you, sir, for your clear explanations. I hope that all the participants would have gained the knowledge on this topic. I assure you, sir, that it would help, especially for young researchers, to proceed further in this area. I thank all the participants for their active participation. Feedback link will be sent to your registered mail ID. Thank you all. We shall meet tomorrow at 2 p.m. for the second day of National Webinar Series 2 on the topic Variants of Graph Coloring and Their Applications. Once again, I thank you all. Have a wonderful day. Thank you, sir.